Hello, everyone. Welcome. So let's start. I think we have a couple of slides that I will hopefully go through, and then we have to be quick. Anyway, so hi, I'm Enes, and I'm a committer and PMC member at HBase, Phoenix, and Hadoop. I've been with Hortonworks for more than 4 years now. Here's my Twitter, and big disclaimer, I'm not a SQL expert, but I'm quite familiar with the Phoenix ecosystem and its development and everything. And we have a big team in Hortonworks working on Phoenix nowadays. So the outline of the talk is divided into 3 parts. The first part, we'll talk about the existing features in Phoenix. We'll cover the basics, the architecture, and we will do an overview of why Phoenix does things certain way, and then what makes Phoenix what makes Phoenix user-friendly in terms of the HBase users. And then the second part, we will go over the recent development in Phoenix. We'll go over what's there in recent releases. We'll go over transactions, Phoenix Query Server, and we'll go over some other features that has been developed. And then we will cover some of the feature-looking stuff that's coming in the upcoming releases, mainly Calcite and Phoenix Hive integration. All right. So, obligatory slide. This is who uses Phoenix. As you can see, Salesforce, Intel, Huawei, eBay, a lot of well-known customers and users are using this for sure. So just to cover the basics, I hope that most of the audience is familiar with HBase. I was just joking that otherwise you're in the wrong talk. But we'll cover some HBase basics, but not too much. So at least it assumes some HBase familiarity. I want to talk about why Phoenix has been developed and why just pure HBase is not enough for most of the use cases. So HBase is kind of like a powerful and flexible and extensible engine that has been talked before. It's kind of like I develop HBase daily, and I know how to use it well and everything, but it's usually described as hard to use and everything because it's kind of like it has a very powerful byte array to byte array and sortable byte array engine that if you know how to use it well, you can do amazing things with it. But it's usually the case that to do this, it's kind of you have to basically write Java code to do most of your stuff. You have to either write a filter yourself, you have to do aggregations yourself, you have to do coprocessors, to do really powerful stuff. And basically, you interact with it using the Java programming API, right? So if you're not a Java guy or you don't want to code yourself, HBase is usually too low level for most of the users. So that's why Phoenix is very, very important for new use cases, because it enables HBase to achieve the next level of usability, because it's kind of like it's an SQL layer that everybody is familiar with, and then also the tooling that has been developed over many decades for SQL is directly applicable to Phoenix and HBase in general. And it's kind of the first mantra for HBase has been for Phoenix. Is described as a SQL skin, but nowadays it's turning more and more into a generic SQL engine. And people usually ask me why it's not Hive or Spark SQL or other SQL over Hadoop solution and not Phoenix. And I usually tell them, like, Phoenix is more like OLTP. It's not like OLAP kind of solution. And if you're doing OLAP analytics and everything, you can use Hive, Spark SQL, or anything, the other MPP databases. But the thing is that with Phoenix, you can do a 1 millisecond query that no other database engine like Hive or Spark SQL can do. And you can do like 10K or 1 million queries per second with Phoenix because underlying it's all HBase, and then you can do point lookups and everything with Phoenix. All right? So why SQL in the first place? So again, as I told, Phoenix enables new use cases because it is SQL. And as you can see, like this is how you would code the same thing in using the HBase's Java APIs versus this is how you would do the same thing in Phoenix. Obviously, this is much more readable and everything, right? But you can do the same things and everything else that Phoenix does using HBase, but you have to, in most of the cases, you have to code it yourself. All right. The second reason that, again, Phoenix enables more powerful use cases is that you can use existing tools for doing BI. You can use existing tools for doing like Excel, for example, like Tableau, like MicroStrategy over Phoenix without any code changes in any of those. So, for example, this is Zeppelin, which is the Phoenix view, and then you can create this kind of powerful graphs with just writing your query yourself instead of having to write the Java code to do all of these, right? This is the power of SQL. So let's come back to the Phoenix architecture. But before going into that, I want to cover the HBase architecture. So quick. Let's say you have an application, and then the application uses the HBase client on the client side, right? You have your regular Zookeeper query that the client talks to, and then you have your region servers sitting on top of the data nodes, right? And then you have the table split it into different regions. So let's say your table foo, there's a region here, region A here, region C here, region D here. And you can have other tables distributed out throughout the cluster, right? And then the client just goes and talks to these region servers directly, right? This is the regular HBase architecture. So when Phoenix is in the picture, the Phoenix architecture looks like this. So the blue boxes here are the Phoenix client or the Phoenix parts. So your application directly embeds the Phoenix client, which is a JDBC client. So your application talks over JDBC to Phoenix. And Phoenix internally uses an HBase client, which talks to the same region service as well. So the actual transport layer between the Phoenix and the region servers are piggybacking on the HBase's regular RPCs. But Phoenix itself has the client component, which is the JDBC and the query driver. And also Phoenix has the server-side components, which implements an RPC endpoint in the region servers, as well as what's called the coprocessor endpoints in the tables. So in the same cluster, you can have pure HBase tables, as well as you can have some of the tables which are Phoenix enabled. And then the Phoenix client will talk with these guys over its own RPC endpoints and also the coprocessor endpoints here. Also, in Phoenix enabled clusters, you will have the system catalog table, which is a regular HBase table, but this will contain all the Phoenix metadata that's needed. All right? All right, so Phoenix obviously comes with a lot more goodies. So some of the examples are like obviously SQL data types and all the DDL statements and schema management that comes with the SQL layer. So you don't have to deal with the HTable descriptor and HColumn descriptors and everything. You can just write the create table statement in Phoenix, and then it will get converted into an HBase table. It has composite types and also has composite primary keys. So you can have multiple columns combined into the HBase row key, which is very powerful. We'll cover all of these. Obviously, you can map existing HBase tables into Phoenix tables. So you can even do something like write from HBase but read from Phoenix. So this enables some use cases where like you want really high throughput writes but you want to enable like analytical kind of queries or like ad hoc queries on top of the existing HBase tables, so that Phoenix enables this kind of use cases. Obviously, the other use cases that most of the users want is all already built into Phoenix, like sorting, parallel scans, skip scans, and filter pushdowns are all built into Phoenix that we will cover later. And Phoenix also has statistics collections and guideposts for basically driving down the SQL queries. All right, so we'll go over an example, and we will cover most of the features that we see here. All right. So this TDL example, it's standard SQL. Create table if not accessed. This metric record table, and then you give the bunch of columns. Let's say this is a metric record table which keeps track of some server metrics emitted with the metric names, the host names, and the server times. All right. And then the metric value is just a double that we emit from the servers. All right. And then here you can see that this is a primary key. We are giving a primary key, which is metric name, host name, and the server time. So these three columns together are concatenated into being a primary key. And then this metric value will become the actual data. That's not part of the primary key. And then you can also do like other stuff like TTL, data block encoding, compression. That these are HBase features, right, which are enabled from the higher level Phoenix query language. You can even do split on, and then you can give the split points that you want, which will create. We are giving 3 split points where it will create 4 regions for us, right? So in terms of the data model, right, it will like logically, this will all be mapped to something like a relational database table. The difference would be that obviously this is mapped into the HBase's data model. So it's not a one-to-one mapping between the relational data model versus Phoenix model, because we are not going to cover that. But for example, you can have dynamic columns that HBase provides, and Phoenix can query the dynamic columns on demand. But anyway, coming back to this, this would be like a standard example of our previous metric record table. Like the metric name will be, let's say, read request count, and everything. And then the host name would be the host name, and then server time would be the actual epoch time. Let's say the metric value is some value. So obviously, HBase is a sorted map. So there are actually 2 sort orders. So everything will be sorted from left to right, and everything will be sorted from top to bottom, right? So this is very, very important, because when you're accessing data in the HBase's sort order, it would be very efficient to fetch this kind of data in the same exact sort order that you would want. And then when I was talking before about the primary key here, as you can see, the primary key is composed of the metric name, host name, and the server time, right? So in this example, the primary key would be metric name, host name, and server time, which will become the HBase row key to the underlying HBase table. And then the other columns would be another HBase column. All right. So to cover some of the Phoenix features, let's look at some of the example queries, and then their explain plans, and then I'll cover how they're getting executed. So for example, this simple query, right? Select star from metric record. Let's say we have created this table, the same exact metric record table using 4 regions. These 4 regions will be distributed out throughout the cluster in different region servers here, region server 2, region server 1, region server 3. And the region servers will host 1 or more regions of the same table. So when you execute this query and look at before even executing, look at the explain plan, the explain plan will say something like this: client 4 chunk parallel 1-way full scan. So what does it mean? What it means is that it's doing a 4-way parallel scan over all this table. So you're automatically getting parallel scans driven by the client, and then the scans will be executing from the region server. So in the end, you would basically, these scans will be driven out by the client, and the client will return the results in the same way that the region servers are returning the results to you. All right? So this is an example of the parallel scan. So to get to the next level, let's look at how filter pushdowns are implemented, right? So you're doing the same query, select star from metric record, but let's say there's a where clause, and you're saying that server time should be bigger than now -7, which means that it has to be, the server time has to be in the last 7 days, right? So when you look at the explain plan, it will say something like this. It's a client 4-way parallel scan, same as before, but it will say server filter by, and then this is the filter. So what does it mean is that instead of the client doing all the scans in parallel, returning all the data, and then client applying the filter, instead this server-side filter, this filter will be pushed into the server sides so that the server side will apply the filter in a coprocessor, and then the client will only return, the server will only return the data that passes the filter by, so that this communication is as efficient as it can be, right? Next feature, skip scans. Skip scans are very important for some use cases, and it's enabled by default in Phoenix, and it's implemented something like this. So let's say you do the same query where you're selecting from some metric record table, and then you have a condition like this. The metric name should start with ABC, right? And the host name should be host 1 or host 2, right? So this is a standard query where you can have thousands of servers, but you're only interested in the metric, some of the metrics in some host names. So the scan, the scan, instead of doing a full table scan and applying the filter one by one over the rows that doesn't even match the scan, Phoenix instead will do what's called a skip scan. So the skip scan explain plan will say something like this. I'm doing a one-way scan, one-way skip scan on 2 ranges over metric record table, which falls into this range. So ABC host 1 and ABD host 2. Where does ABD comes from? It knows that the next matching string after ABC is ABD. And then it knows that I'm only looking for host 1 and host 2. So remember in this example, everything is sorted by the metric name first, and host name second, and server time third, right? So in this, the skip scans will will skip to the first ABC host 1 from the server side, and then it will only scan as long as we are still matching in this range. And after the match is finished, it will seek to the next available match, which would be ABD host 2, right? So it will actually, this scan will actually skip the records that it knows where to skip, and it computes the next skip point using the H file indices that's stored in the H files inside the regions, right? All right. So let's look at a top-end example. It's another example where most of the HBase users will need something like this, but it comes enabled by default in Phoenix, right? So let's say you're doing select star from metric record where server time is this, and you want to order by the host name, and you want to only get the top five matches, right? So the way that Phoenix computes this query, if you look at the explain plan, is that it will say something like this. server filter by something something, server top 5 rows sorted by the host name, right? And then it will say client merge sort. So what happens is in this query plan is something like this. So the client does a 4-way parallel scan, and each of these scans will apply the server-side filter, which is this. And then at the end of the matching results, it will do an order by the host name. So it will do a sort, and then it will only return the top 5. So every scan result, instead of returning all the data that matches, it will do the sort, and it will only return top 5 rows from every region. So the client receives 20 rows in total. It does a merge sort from all of these results, and then it will give out only the top 5 matching, which is the most efficient way you can execute this query, right? Another look at an explain plan for aggregation would be something like this. Let's say you're doing the same kind of query, but let's say we want to get the average of the metric value grouped by the metric name and host name. This is a very, by the way, these are taken from actual queries that has been developed as a part of the Ambari metric server, but these are mostly simplified versions, right? So let's look at this. We're going to select metric name, host name, and average of the metric value. And then we're going to group by metric name, host name, and order by metric name, host name. So this is a standard query where you would want to get the average result of the last 7 days based on the metric name and the host name, right? So the way that this query is executed would be something like this. So we're still going to do a 4-way parallel scan and apply the server-side filter as usual. And then, but we will do a server-side aggregation into ordered distinct rows by metric name, host name. So what happens is that the server side does the scan, and while the scan results are going on, it's going to execute an order by and group by at the same time, and only return the results of the aggregate data to the client. The client still will do a merge sort of all the results coming in from the server sides, but the returned result will only be the aggregated data. So if these are like 1 million records, for example, each, the returned results will only be like the aggregate data by metric name and host name. So it will be like, let's say, thousands of rows instead of millions of rows for this case. All right? So obviously, Phoenix has much more stuff than what we have explained. It has joins and subquery support. So for joins, Phoenix supports inner joins, left, right, and full outer joins, cross joins, semi-joins, and anti-joins. We won't go into details of any of these for this talk. It also, in terms of the algorithms that it supports the hash joins and sort merge joins. So hash joins will be implemented something like the hash join table is computed from the client side, and the hash join table is sent out to all the servers that the query has to hit, and then the probe table is scanned with this hash table, and then the join is executed on the fly, right? And it has predicate pushdowns for the joins. This is actually, there's a typo here. Full primary key to foreign key join optimization is there. Global index with missing columns optimizations and correlated query rewrite kind of optimizations are there. So, I think this is a very exciting thing. Like Phoenix can execute most of the TPC-H queries, which is a recent thing. But there's still some limitations in the join support, like there's no nested loop joins, and there's also no like statistical guided join selection yet. But it's like more stuff is coming with the Calcite integration, and that we're gonna talk about it in the part 3 section. And Phoenix is not known to basically be very good at executing very large joins. But it has excellent support for Spark and it's also Hive support is coming. So Phoenix tables can be defined in Spark and also Hive, so that you can execute the join in Spark or Hive from the Phoenix table data. All right. Phoenix also has secondary indices like you can define a global index or a local index in Phoenix, and then since everything in HBase is a sorted map kind of thing, the secondary index would be another sort order for the for your data. So when what you do is that like when you define an index on top of an existing table, what happens is that if it's a global index, we will create another table for you, and another HBase table for you, and then that HBase table will have the sort order that you define for your secondary index. So since we will have two different, let's say the primary sort order and the secondary sort order, then we will access the data using the secondary sort order or the primary sort order. This is how the efficient secondary index access will work, right? And the indexes are covered indexes, so like you would the data will be replicated in the secondary index, so that you can actually access these the columns that you want from the query using only the secondary index table data. You don't have to go back to the primary data to get the information again, right? And the indexes are automatically selected from queries, but you can also hint using the secondary indexes. Also, we covered the covered columns, what's called covered columns, that the query, if the query hits all the covered columns in the index, they will automatically be returned from the covered data, right? And as I said before, Phoenix has a concept of a global index and a local index. The global index is usually read optimized versus the local index is write optimized, right? And you can think of the local index as like a mini instance of the index per region. So what happens is that in the local index, we use the same HBase table to store both the primary data and the secondary index data. And we can do atomic commit and visibility for the local index. But we can also do the same thing using transactions in the global index case. All right? All right, so let's go over the present and all the recent stuff that Phoenix has. So we won't have the time for going over all the details of these new features, but you can basically reference them later. So 4.4 release is kind of like a recent release that Phoenix community pushed for in the last year. It has functional indexes, UDFs, the query server is there, union support, MapReduce index build, Spark integration, and date functions. 4.5 comes with like client-side per statement matrix, select statements without from statements, alter tables with views, and a bunch of math and array-related functional improvements. 4.6 came with the row timestamp, which we will go into details. It has support for correlated variables, support for unnested arrays, and a web application for tracing data. 4.7 is the most recent release. It comes with the transaction support, secondary index improvements, and statistics improvements and performance improvements there. All right? So the row timestamps is an interesting feature that has been recent. So you can think about the row timestamp as a pseudo column in Phoenix, but it's there so that the HBase native timestamps are surfaced inside Phoenix. So what happens is that you can declare a column, which is the, let's say, created date as row timestamp inside your Phoenix definition. And this column, this pseudo column, will be automatically mapped to the HBase timestamp, which is how HBase keeps versions of your data, right? So this is very, very good for time series kind of use cases where you can combine this feature with the FIFO data compaction policies that's recent in HBase to get like to solve your time series kind of use cases very, very efficiently. And also, like since HBase can do like scan file pruning based on your timestamps, when you can actually declare a table like this and do a query where you can say created date should be less than this and greater than this, then HBase will automatically filter out all the files that it shouldn't see because of the time ranges, doesn't fall in, and then it will execute the scan very efficiently for you. All right. So transactions is another feature that's been recent in 4.7. It uses a project called Tephra, which is also now in incubation, Apache incubation. Tephra implements snapshot isolation for HBase. You can use it with or without Phoenix, obviously. So it's kind of like it's a layer on top of HBase that you can use, but Phoenix transactions has been implemented using Tephra as a library, right? So these are this implementation is now completely optional. So you can enable transactional table by setting this value at a per table level, and then you can have transactional and non-transactional tables at the same Phoenix cluster, right? The transactions can see their own uncommitted data, and it does implement the optimistic concurrency control. So there's no lacking in executing the transactions. But obviously, in case of like there's high conflict, then the conflict resolution is much more costly. So basically, the transactions, if there's a conflict, it has to roll back the transaction and undo the changes that it has done before. It has been released in 4.7, and it will go GA in 5.7. All right. So this is the main Tephra architecture. As I was telling, it's completely independent of Phoenix, so you can even use it without Phoenix, and it uses what's called the Tephra HBase client, which is kind of like a transactional client that knows about how transactions work and everything, and this provides the higher level transactional API. So there is an active standby transaction manager, which is a single node, and then it keeps its metadata in Zookeeper, and the client does talk to the transaction manager for every transaction, right? And here is the transaction lifecycle. I don't think we will have the time to go into details, but short summary is that the client at the start of the transaction will talk to the transaction manager, and then transaction manager will give a timestamp back, and then the client will do some work in terms of does the writes and reads for the transaction, and then it will try to commit back the transaction to the transaction manager. If there are no conflicts, the transaction is committed. If there are conflicts, then we have to abort and undo our work that we did for the transaction. All right. So Phoenix Query Server is another recent feature that has been implemented and that has been shipped in 4.7 and before. So it's similar to the HBase's REST server, or if you're familiar with Hive Server 2, it's similar to that. It's built on top of the Calcite's Avatica server, but it has Phoenix bindings, and it embeds the Phoenix tick client inside. And the good thing about the Phoenix Query Server is that there's no client-side sorting, there's no joins or anything if you are using the Phoenix Query Server client inside. So the protocol is protobuf 3 over HTTP, and it has a thin JDBC client that's different than the regular Phoenix client. All right, and it also allows ODBC driver for Phoenix for the feature. So this is the standard Phoenix architecture that we talked about. There's the application, there's the Phoenix client, JDBC, and HBase client talking to the region service, right? So in terms of the execution, for example, the Phoenix client can do sort merge joins and other executions that may be costly, and you may not want that to execute in your client-side code. So the Phoenix Query Server fits perfectly in that because you can actually have the Phoenix Query Servers, which you can deploy as many as you want. And then the regular Phoenix client, shown in blue here, is embedded within the query server. So this is the regular Phoenix client, but it's embedded inside the Phoenix Query Server. So instead of using this client in your application, you would use the thin client, what's called the thin client in your application. This is a real thin client that would just delegate all the work to the Phoenix Query Servers. And then this is the HTTP, protobuf HTTP transport. And then the Phoenix Query Server will execute the query and run the Phoenix client for you. And then if there is a client-side merge sort, this guy will execute the query for you. All right? So other good features that's coming in for that 8 plus is shaded client. So this has been a problem in the Hadoop ecosystem overall, and it's been solved in HBase already, and Phoenix we're solving it as well. There will be shaded client will be by default, and there will be no unshaded version. The Phoenix schema mapping to HBase mapping is coming. So you would be able to create schema foo and use foo as usual. Like this will be mapped into an HBase namespace. And limit offset is also coming. So we already had limit support, and now we will have offset support so that like you can do MySQL like limit offset kind of queries. Together with the row value constructs that we didn't go into, this covers kind of like cursor or pagination kind of use cases. Right? All right, the feature. So there has been a lot of local index improvements recently that we have been trying to push. So local index has been re-implemented. Instead of being a different table, now it's the same table but hosting in a different column family. And the index and data is committed together as a single transaction without any more like external transaction support. So this will be super efficient for writes. So the local index would be the performance impact for getting local indexes would be minimal in terms of the write throughput. So if you have like super high write throughput use cases, local indexes would be perfect for this. Calcite integration is also coming. I think this will come in 5.0. So Calcite is a framework for query parser, compiler, planner, and cost-based optimizer. It's a SQL 92 compliant framework. It has all the features. And it's based on the relational algebra, and it has the cost-based optimizer with some default rules, but it has a pluggable rules backend that Phoenix plugs in its own rules so that the Phoenix Query Planner will work together will work on top of the Calcite's rule engine, right? It's already used by Trail, Hive, and Kylen, and Samza, and other projects as well. So it's a very mature implementation. So here is how it will work. The JDBC client for Phoenix will use the Calcite parser, and then the SQL and Phoenix-specific grammar will go in the Calcite parser. And then the Calcite query optimizer, obviously, as I talked before, will use the built-in rules plus the Phoenix-specific rules to come up with the query plan. And then the query plan will be generated by Calcite using these Phoenix-specific rules. And then the Phoenix runtime will run those. All right? So the Hive integration is also coming. Hive is obviously a very rich engine which has test support and then can execute arbitrary DAGs, right? It can do big joins and other features so that the Hive integration into Phoenix will have, we can use all of these Hive features, all right? So there will be Phoenix DDL support in HiveQL, and also like data DML support, as well as predicate pushdown, salting, and partition pruning and everything will be automatically taken care of because the integration uses already the Phoenix compiler to compile the query plan inside Phoenix as well. So there will be 2 levels of compilation. The Hive will compile the query, as well as Phoenix will compile the query. All right, so you can get more information in this Jira if you're interested. So there's even more Phoenix features that's in the works. There's JSON support and TPCH, MicroStrategy, or Tableau kind of queries, like executing these in the Phoenix test suite, so that like you would know that these will work out of the box with Phoenix. Scope integration, omit-based transactions is coming. Struct typed improvements to cost-based optimization is also coming. Security and other HBase features being surfaced from Phoenix is also very important. There's an official roadmap here. You can go check it out. Also, there's some dogfooding within the Hadoop ecosystem. Nowadays, the Ambarometric server already uses Phoenix. And Yarn will also soon use HBase and Phoenix for the ATS, the application timeline service. All right. This is just for reference. You can get more information in the official Phoenix pages. And if you're interested, obviously, join the mailing list for more discussion. All right. I don't think we have time for Q&A, but there will be a HBase Birds of Feather session starting at 5:30. So you can come over there and then ask. You can ask questions, or you can catch me offline for more questions. All right. Thank you.